Okay, good morning, everyone. Okay, apologies, I'm a few minutes late. I hope you're having a better morning than me. My car broke down on the way here today, so I'm surprised I'm even here. You guys nearly got off scot-free, but sorry, I did make it in. Also not done my prep ahead of today because I broke down, so let's see how we get on. Okay, so just a reminder that the content for today and Friday and Monday of next week are all on nonlinear systems of ODEs. And these nonlinear systems of ODEs will appear on the final, but they're not going to be on the midterm of next week. Okay, so I did send out an announcement about the midterm as well. Let me know if you have any questions, but I will push on for now. So essentially, the stuff that we've done on linear systems, we're going to be applying a lot of those same principles to nonlinear systems as well. Okay, and most of the stuff that we see in nature is nonlinear. Linear systems are very special things. But most of the stuff we see in nature is nonlinear. In the pre-lecture, there's this example of predator-prey systems. This is a very classical example in mathematical biology, where records of lynx and hair pelts have been kept for decades, going back to the mid-19th century. And when they looked at these data, they saw that there were these fluctuations, these population cycles in predator and prey density. And this led to something called the Lotka-Volterra predator-prey model, which is one of the simplest nonlinear models that we have in mathematical biology. So what is a nonlinear model? Well, we have general functions f of xy and g of xy on the right-hand side of our equations. Previously, these were linear, so we would have something like our f of xy would equal ax plus by, and our g of xy would equal cx plus cy, where ab, cx plus dy, that should be. A, b, c, and d are just some constants, okay? And because they're just constants, these are linear, and so we'd be able to write this in matrix form with coefficients a, b, c, d, okay, as our matrix. So this is what we've been doing up until now. Now, though, we're going to be thinking about general nonlinear systems. So that means that, for example, we might have x squared terms in here, you might have xy terms, there might be exponentials or whatever, okay? So they're no longer linear, which means we can't write them in that same matrix form. Okay, so the pre-lecture introduced the Lotka-Volterra model for predator-prey systems and then went through some of the analysis for it. Key steps of the analysis are basically the same for the linear problem with one key difference. First of all, we find our null lines. So we set our dx dt, our dy dt equal to 0, and then solve them. Now, when we did this for linear systems, we would, because they were linear, we always ended up with a straight line, and we just have one null line for each of our equations. So one null line corresponding to x and one null line corresponding to y. Now, because these are non-linear, they could be anything, and we could have any number of null lines. So that you could have 1, 2, 3, 5, whatever. You could have quadratic things in there, you could have exponentials, anything, okay? So now when we solve these, we need to be solving more general equations. For the most part here, we'll be dealing with things that are quadratic. So in this case here, we end up with 2 null lines for x and 2 null lines for y, okay? In this case, they all happen to be straight lines, but they're no longer just straight lines that say on the axes. Recall that whenever we have a null line for dx dt intersecting with a null line for dy dt, that means we have an equilibrium. So here I've color-coded. I'll generally try to color-code my null lines so it's clear. We have here an intersection between a blue and a red line. So that means we have an equilibrium. Likewise here, an intersection between a blue and red line, which means we have an equilibrium. We don't have an equilibrium here because these are 2 blue lines. Likewise, we don't have an equilibrium here because these are 2 red lines. Okay, so we only have equilibria where we have an intersection of the 2 different null lines. So for one for dx dt and one for dy dt. We can draw phase planes as we see here. Previously, all of our dynamics, because we only had one equilibrium, it was focused on the origin. Now here, we can be anywhere. If these are population models, though, which for the most part, we are going to be focused on population sizes, we're going to be thinking of non-negative values for x and y, okay? So that's why I'm only in this first quadrant here, and I haven't drawn negative values of x and y, because we don't care about negative population sizes, because they're not biologically realistic. So we find our null clients, and just as we find our null clients, we can also find our direction field using the same methods that we did before. So look on a null client, substitute that null client into the other equation, and then that will give you the direction field. So just like we did previously. So an equilibrium in a general system is just some pair of values x star, y star that satisfy dx dt equals 0 and dy dt is equal to 0. That's just formalizing that. And then the new thing that we're going to introduce here is something called the Jacobian. So this Jacobian matrix, what we do is it's the matrix of partial differentials of our system. Okay, so on the first line, we take our first function. So we have dx dt is equal to some function f of x, y. We take the partials of that with respect to x and with respect to y, and then we put it on the first row. And then we do the same with our partials for g of x, y, where we have dy dt is equal to g of x, y. We take our partial with respect to x, partial with respect to y, and put it on the second row. So the pre-lecture went through on this slide here why we care about the Jacobian. You don't need to remember this for an exam or anything. You're not going to be examined on this. This is more for background to justify why we're doing this. The key thing is we are looking in our nonlinear system at a particular equilibrium, and then we're going to move a tiny bit away from that equilibrium. Okay, we call that a small perturbation. So we have this small perturbation, and then we're setting up a system here to look at whether that perturbation grows with time or whether it decays. Now, if it grows with time, that means we're moving away from our equilibrium, and so it's unstable. But if that perturbation decays with time, then we're moving towards our equilibrium, and so it's stable. So what's happening with this perturbation tells us about the stability of our equilibrium in general. And it turns out that, as we've done previously with our linearizations, if you zoom in enough on something that's nonlinear, it starts to look linear. And that's what we're doing here. We're turning our nonlinear systems, which are difficult to deal with, into lots of little linear systems at our equilibria. Okay, so we end up with an equation down here where we have dx dt is equal to j times by x, where x is giving us our perturbation. Okay, and j is just a matrix. It's a matrix of partial differentials, but at the end of the day, it's just a matrix. It's evaluated at the equilibrium, so it's just a set of numbers or set of parameters like we would have in our linear systems that we've been looking at the last few times we've been here. So this is telling us whether those perturbations are going to grow or decay. So all we need to do is now analyze these linear systems in sequence. So at every one of our equilibria, we look at the Jacobian, we calculate it. We can calculate a general Jacobian and then just substitute those values of the equilibria in. And then we can look at the trace and the determinant, or we can calculate the eigenvalues to figure out what type of stability we have. It's exactly the same stability diagram that we had previously. Okay, that is a summary of the pre-lecture. Do you have any questions before we go on to problems? Nope. Okay. So like I mentioned, we're going to be doing lots of phase planes, and the stuff we learned from linear systems, we're going to be doing in nonlinear systems. So practice, practice, practice. And it won't surprise you that they probably might appear on the exam. We're going to focus in these 3 lectures on nonlinear systems on a few different contexts for why we care about these things. And the first one is in disease modeling. So this is why I'm in Canada. I'm a disease modeler, and you may have heard that there was a pandemic. And so I do lots of disease modeling. It's really similar to this kind of thing here. It's a bit more complicated, but the same foundational principles are that we're breaking up a population into different compartments. So these are called compartmental models. And here we're breaking up a population into individuals who are susceptible, S. They're infected, and here infectious as well. And then they are recovered or removed from the population, and they're immune. So we can think of what's called a transition diagram between these different classes. So we move from S to I when you get infected. You move from I to R when you recover. And then in this case here, we also move from the R to the S class at a certain rate. So this, in this case, corresponds to waning immunity. So this is where you might have immunity for a short period of time, but that immunity decays and then you become susceptible again. So this is a type of model. This is an SIR model, or sometimes this would be called an SIRS model because we go back to the S class. And there's lots of different types of models that are built on the same principles of breaking the population down into different compartments and then thinking about the flow of individuals from one compartment to another based on epidemiological processes. So we can have an SIR model. There's something called an SEIR model. And that's where you have an exposed class where people are infected but not yet infectious. We can have an SEIRS model where there's waning immunity as well. We can introduce population demographics, so things like births and deaths. You can have asymptomatic classes and symptomatic classes. You can have people who are hospitalized and not hospitalized. You can have high risk, low risk, and so on. There's lots of different things you can do to extend these models. And that's what a lot of the pandemic modeling has been based around, thinking about extensions of this type of model here. Okay, so if S of t is the number of susceptible individuals at time t, and I of t is the number of infected individuals, and R of t is the number of removed or recovered individuals, we can think about what is the meaning of these different terms in our model. So I've mentioned this AR already. This is the rate that immunity is lost. In other words, our waning immunity. So A is just some parameter here. These are all positive parameters. And it's telling us the rate at which individuals go from R to S. So this is waning immunity. But CI, well, CI is going from our infected class to our recovered class. So this is going to be recovery. This is our rate of recovery. And this rather complicating looking term here, KBSI. Well, we can break this down. We know that this is going from our S class to our I class. So this has to be infections. Let's break this down. So if we think about this I over N term, this is telling me the fraction of the population that is infected. So this turns out to be our probability that when we come into contact with someone, they're infected. We have our S here, that's just a susceptible individual. So we have a certain number of susceptible individuals and they're coming into contact with infected individuals. So the number that we're going to be removing is going to be based on the number of S individuals. So these are our susceptible individuals. This B and this K, well, we don't know what each of these things mean, but if we define our K to be our contact rate, it's the rate in which individuals come into contact with each other in general, and B is our probability of transmission given contact, then this whole thing here is saying, okay, we have a contact rate, we have individuals coming into contact with infected individuals with a probability I over N. And given that they come into contact with an infected individual, there's a probability B that they will be transmitted, there'll be transmissions, they'll be infected, okay? So we can break this term down here. Ultimately, this comes down to be our infection rate, the rate at which new infections are being produced. Okay, so let's do a little bit of analysis on this model. So I want to start by showing that the number of total people in the population is conserved. So what do I mean by this? Well, if I let N be the total population size, we've already got an N up here already. Everyone must be either susceptible, infected, or recovered. So if we add these three things up, what do we get? Well, let's think about the rate of change. If our total number of the total population size is conserved, that means our dNdt has to equal 0. So let's add up our dSdt, our dIdt, and our drdt. You know, going back to this diagram up here, this transition diagram, there's no arrows going out of the boxes or coming into the boxes from nowhere. So there's not an arrow like this where people are just disappearing. So we should have this flow where everyone is conserved. Okay, so let's add these things up. We're going to have an AR minus KB SI over N. That's our ds dt. We have a KB SI over N minus CI in our di dt. And then we have a CI minus AR in our dr dt. It should be pretty clear that these infection terms cancel, these recovery terms cancel, and then the waning immunity terms cancel. So that means our dn dt is equal to 0. So the population size overall is not changing. So the population size is constant. Why does that matter in this case? Well, if the population size is constant, we know that n is equal to s plus I plus r. We have 3 equations here. If we want to try and analyze this system using the tools that we have, if we just do it now, we're going to have to write down a 3x3 matrix. We don't like dealing with 3x3 matrices because they're more complicated. We like 2x2 matrices. But because we have this relationship here, we can eliminate one of our variables. So in this case, I'm going to eliminate r by writing n minus s minus I. So if we know the number of individuals who are susceptible, we know the number of individuals who are infected. Because we know the total population size is n, we can immediately work out the last one. Okay, so if you have 2 pieces of information, you can work out the third. That means we can rewrite our system now as ds dt is equal to, we had AR before, so now we just substitute in n minus s minus I. So this was our r that we had previously. We had an infection term, KBSI over n. That doesn't change. And our di dt, that doesn't change either. We have KBSI over n minus CI. And because we know what r is, we don't need dr dt. So this means that we've reduced our problem from a 3-dimensional problem to a 2-dimensional problem with just these 2 equations here. Any questions so far? Yes. Sorry, a little bit louder. As in to remove here, this, why did I choose R? Yeah. It's arbitrary. I could have chosen any of them. We tend to, if possible, take out the R because it's the slightly less interesting one. We kind of care who's currently susceptible, who's currently infected. We care a little bit less about who's removed from the population. That's a convention thing, but there's no, it wouldn't be incorrect to get rid of S or get rid of I if you wanted to. It also makes it a little bit simpler because if we tried to get rid of S or I, because the S's and I's appear in these terms here, and we're multiplying an S by an I, that's going to make it a little bit more complicated. So the R only appears in a linear term, which makes it a little bit easier to analyze. That's the other reason why we choose. Any other questions? Okay, so let's think about our fixed points. Fixed points are the same as equilibria. So I defined the fixed points for this SIR model. So it's the same as above, basically, but now it's got a few different numbers in here rather than parameters. The structure is basically the same though. So how do we find our fixed points? Can someone remind me? Anyone? Come on, guys, I know you can talk. We need to set one of these equations, then the other equation equal to 0, okay? So this is just like finding our null lines. When our null lines intersect, we have equilibria, so that means that we need both ds dt and the idt equal to 0. So let's work through this one together. So di dt, I'm going to start with this because it's a little bit simpler. This one is equal to 0 when this equation here is equal to 0. So this tells me that we need 1 over 1,000 SI minus a half of I equal to 0. Now, since there's an I in both of these terms here, we can factor that out. And it tells us that either I must equal 0 or 1 over 1,000 S minus a half must equal 0. So if we factor out that I, we know that I has to equal 0, or the thing will be in the brackets, which is 1 over 1,000 times by S minus a half must equal 0. So if we rearrange this here, this tells us that S has to equal 500. So we know that for di dt to equal 0, the change in the number of infected individuals to equal 0, we either need there to be no infected individuals, or we need there to be 500 susceptible individuals. Okay, now let's think about what happens if I is equal to 0 and ds dt is equal to 0. I'm now setting the first equation equal to 0. I'm substituting in I is equal to 0. Okay. So in this case, we have 500 minus a half of S minus a half of I, but I is going to be 0, minus 1 over 1,000 S times by I, but I is 0, and this is equal to 0. So if we cancel out those zeros, we get 500 minus a half of S must equal 0, implies S is equal to 1,000. So we know one of our fixed points already is going to be S is equal to 1,000, I is equal to 0. So now we do exactly the same, but rather than substituting I is equal to 0 into our ds dt is equal to 0, we're going to substitute this value here, S is equal to 500. So if S is equal to 500 and ds dt is equal to 0, we're going to have 500 minus a half of S, which is 500, minus half of I, which we don't know yet, minus S, which is 500, over 1,000 times by I. So we have 500 minus a half of 500, so that's going to be 250, minus a half of I, minus 500 over 1,000 times by I, so that's again minus another half of I. So we have 250 minus I is equal to 0. Take the I to the other side, gives us I is equal to 250. So whenever you do this, you find your equilibria by substituting, well, by setting both of your equations equal to 0, set one of them equal to 0, find whatever values, in this case of I and S you have, and substitute those into the second one when it's equal to 0. Okay. So it's just like solving simultaneous equations. At the end, it's always good to try and summarize what you have. So what are our fixed points? We have SI is equal to either 1,000, 0, or 500, 250. Okay, a mistake that people often make is they put all combinations of these things down, but the only combinations we have are if S is equal to 500, I must equal 250. Those ones in yellow. And if I is equal to 0, then S must equal to 1,000. We don't have S is equal to 1,000 and I is equal to 250. We don't have S is equal to 500 and I is equal to 0. Okay. So be careful of the combinations that you use. Yes. As in here, it doesn't matter. You can write them in whichever order you want to. Any other questions? Okay, so what's the interpretation of these two things? Well, in this one here, we've got 1,000 susceptible individuals and we've got 0 infected individuals. So this is known as our disease-free equilibrium. I'll sometimes abbreviate that to DFE. Okay, this just means there's no disease in the population. In the second one here, there is disease, and this is known as our endemic equilibrium. The endemic here basically means it's just staying in the population. We don't know anything about the stability of these equilibria yet. All we know is that if you are at these points, you will stay at those points, but we don't know what happens if you're near to those points. And that's where our linear stability analysis comes in. Okay. So we've got our fixed points. Now let's look at our analysis of the stability of those fixed points. So I'm going to call this first equation f of Si, and this second one here, g of Si. Remember what I said at the start, what we're going to do at our equilibria is we're going to turn in the neighborhood of those equilibria, we're going to turn our nonlinear system into a linear system, and then use exactly the same tools that we've used in the last 3 lectures to analyze the stability, okay? But to do that, we need to look at our Jacobian. So this is a matrix J, which is going to be a function of S and I, which is our matrix of partial derivatives. We have our partial derivative of f with respect to its first variable, s, partial of f with respect to I, g with respect to s, and g with respect to I. Go back to the question about ordering. It doesn't matter if I put them in the other order, as long as I'm consistent with everything that I do, okay? So the ordering of these things doesn't matter as long as I'm consistent in how I do them. So think about when you're doing a matrix multiplication, when you're setting up those population models earlier in the course with juveniles and adults, you can put adults and then juveniles, or juveniles and adults, as long as you make sure everything is consistent. Okay, so what are our partials here? Well, f sub s, the constant term goes. Then we have minus a half of s, and when we take the derivative of that with respect to s, we just get minus a half. The minus a half of I, derivative with respect to s is altogether 0, I heard someone shout. That wasn't quite altogether, but we'll let it slide. Let's try this again. Minus 1,000 si, derivative with respect to s is... yeah, minus 1,000 I. Okay, so it's just, this is, when we're taking the partial with respect to s, this is a constant and this is a constant, okay? So the s loses its power, goes down by 1, so we add s to the power of 0, which is 1, and then we just have the constant term. Okay, so that's our f sub s. Now we just do this for everything else. Now we do our f sub I. Again, the constant term disappears at the front. We have a minus a half s, derivative with respect to I is 0. Minus a half I, derivative with respect to I is minus a half. And then derivative of the final term with respect to I is minus 1 over 1,000 times by s. Second equation, this one over here, g sub s. There's only one s term here, so you end up with 1 over 1,000 times by I, not s. And then partial with respect to I, both terms are linear in I, so we just drop the i's out. So we have 1 over 1,000 s minus a half. So this is our Jacobian. And this Jacobian is a function of s and I. Because it's a function of s and I, The stability will change when we analyze this, depending on which values of S and I we substitute in. So up here, we have our fixed points in green. Okay. So these are our values of S and I that we're going to substitute into our Jacobian. And then we can look at the trace and the determinant and look at the stability there. Okay. So now we say, okay, at our first equilibrium, so our disease-free equilibrium, we had 1,000 susceptible individuals and 0 infected individuals. What's our Jacobian? So J at 1,000, 0. Just substitute these values in. Minus a half, minus 1 over 1,000 times by 0, so it's just going to be 0. Then in the top right, we have minus a half, minus 1 over 1,000 times by S. S is 1,000, so we're going to have minus 1,000 over 1,000. The 0 in there. The bottom left-hand entry, we have 1 over 1,000 times by 0. And then the bottom right, our S is 1,000, so we're going to have 1,000 over 1,000 minus a half. So if we simplify this down, we have minus a half, minus 3 over 2, 0, and a half. Okay. Now at this point, there's one of two things you can do. You can look at the trace, and you can look at the determinant for a general matrix. When we're looking at our trace and determinant, the reason we do that is because we want to know something about the eigenvalues. And we want to know something about the eigenvalues because that tells us about the stability. But because this matrix is in upper triangular form, so there's a 0 here. If it's in triangular form, so if you have a 0 here, or if you have a 0 here, or both, what that means is that our eigenvalues can be read straight away. So I know that one of my eigenvalues is minus a half. My other eigenvalue is a half. So one is negative and one is positive. I could look at the trace and look at the determinant, but in this case, I don't have to. I can just read the eigenvalues off straight away. So if I've got one positive eigenvalue and one negative eigenvalue, what does that mean that this equilibrium is? What's its stability? Can anyone remember? Saddle? Yeah, exactly. This is a saddle. Okay, if you can't remember or you want to look at it in terms of trace and determinant, in this case, the trace is going to be 0 and your determinant is going to be minus a quarter. So on that diagram that we've had previously, which looks at the trace and the determinant, you'll see that you have a saddle. No, saddles are always unstable. We don't have to say a stable. There's nothing such as a stable saddle. We always have an unstable saddle. It's implied. You don't have to write unstable saddle. What does this mean then? It means that if you were to actually draw this out in a phase plane, you'd see that you get pulled towards the 1,000, 0 in the direction of there being no infected individuals. Okay, so if there's no infected individuals, and say you have 500 susceptible individuals, the population of susceptibles just grows to 1,000. There's no infected individuals there at all. But if there are some infected individuals, you're going to get pulled away from that. So you only move towards this point 1,000, 0 if there are no infected individuals there at all. Yes?
So there's a lot of constants in both equations.
Yeah.
Would that mean that the constants are different? Actually, it would be not stable or stable.
Exactly. Very good question. So this outcome here that we have a saddle is only true because of these particular values. It'll be true for some other values as well, but a key part of when we're doing stability analysis for, say, disease models is understanding when a disease is going to spread and when it's not going to spread. And different parameter values in this will tell us when it can spread and when it can't spread. So very good question. Any other questions? Okay. So here we're going to show that this equilibrium is stable. So what I want you guys to do, we have our Jacobian, I'll leave the Jacobian there. So this same Jacobian applies, as in this one, which I'll highlight here. This is our Jacobian. You don't need to recalculate that again. You just need to substitute in our values for our endemic equilibrium down here, SI is equal to 500, 250. Then look at the trace and determinant and see what happens. Okay, let's work through this one. So to understand the stability at this equilibrium, quiet guys, thanks. We just need to substitute into our Jacobian above, the bit that's the matrix that's shaded green, these values for S and I. So what are we going to have? We're going to have minus a half out of it, minus 1 over 1,000 I, so I is 250. And we're going to have minus a half minus 1 over 1,000 S. So we're going to have minus 500 over S. Sorry, minus 500 over 1,000. In the bottom left, we have I over 1,000, so 250 over 1,000. And the bottom right, we're going to have S, which is 500 over 1,000 minus a half. Okay, so top left, we're going to have minus a half minus a quarter. So it's going to be minus 3/4. The top right, we're going to have minus a half minus a half. So it's going to be minus 1. The bottom right, we have 250 over 1,000, which is a quarter. And in the bottom right, we're going to have a half minus a half, so it's going to be 0. Now, a mistake that sometimes people make is that they think I can read my eigenvalues off here. This is not in triangular form, okay? To have a matrix in triangular form, we either need to have a 0 here, or a 0 here, or special case, in diagonal form, a 0 here and here. Okay, so you can only read off your eigenvalues straight away if it's one of those forms. So at this point, we have two options. We can either calculate our eigenvalues, which is a bit laborious, but if we only care about whether something is stable or unstable and classifying its stability, we can just look at our trace and our determinant. So our trace here is going to be the sum of the elements in the main diagonal. So that's minus 3/4 plus 0. So that's minus 3/4, that's negative. Our determinant is going to be minus 3/4 times by 0 minus a quarter times by minus 1. That's the quarter, so that's positive. Now at this point, the question just said to show that this is stable. If we go back to our diagram, I won't put it up now because I'll have to find it in my notes. Then if we have a negative trace, so we're on the left-hand half of that diagram, and we have a positive determinant, so we're in that top left quadrant of our diagram showing the stabilities. And there it says that we either have a stable spiral or a stable node. So both of those are stable, so actually we could stop at that point. But let's go a little bit further. We've shown that it's stable. Is it a node or a spiral? Let's look at our tau squared minus 4 delta. So in this case, we have 9 over 16 minus 4 over 4, which is minus 7 over 16, which is negative. So if this tau squared minus 4 delta is negative, what does that mean for my eigenvalues? Are they real or complex? On 3, 1, 2, 3. Okay, that's nice. It's nice. We'll get some harmonies going towards the end. So we have complex eigenvalues. Which means that we have a stable spiral. I saw some fist pumping there, that's great. So you got a stable spiral. Okay, so this is a classic thing that we do in math, right? We have some real world problem, we do some mathematical analysis on it. You've shown that you've got a saddle, you've got a stable spiral. What's the actual biological interpretation? So this is the step that people often struggle with, is saying, okay, what does that actually mean in terms of the biology? What is the real world implications for this being a stable spiral? Okay, so let's think about what our epidemics look like. So this is the number of individuals, if we plot the number of individuals versus time t. And And we know that we have this equilibrium at 500, 250. So that looks something like this for our susceptibles and this for our infected individuals, okay? This is my S. This is my S and this is my I, okay? So we know that because this is stable, we eventually end up there. But we also know that this is a stable spiral. So that means we're going to spiral in towards it. Now we could draw a full phase plane at this point and see what direction things are going to go in. We can also use a bit of intuition here. If we have enough susceptible individuals in the population, we're going to have an epidemic. So suppose we are below here, we're below this line here, we reach a certain number of susceptible individuals. At this point, we start having an outbreak, okay? So the number of susceptibles will go down. Okay, so we see some sort of spiral. In fact, this isn't a very good drawing. I'm going to draw it from the perspective of the infected to start with. That's a little bit easier, I think. Okay, so we start off with there not being many individuals infected. We eventually have an epidemic. We're spiraling, so we know that we must be crossing over this line, okay? So we have an epidemic, and then eventually those numbers fall. In this model, because we've got waning immunity, we reach a point where we have enough susceptible individuals again, we get another epidemic, but it's less this time because we've got a stable spiral. Our second epidemic wave is less in magnitude than our first epidemic wave because we're spiraling into this point. So the amplitude is decreasing. It happens again and again. So eventually it will settle down. Likewise, we could draw a corresponding graph for our susceptible individuals. Maybe it looks something like this. So we know in the long term they settle down. We know that we have a stable spiral, so we're spiraling in. What that means biologically is that we're having successive waves of epidemics. And eventually things settle down. But the reason we have these waves of epidemics is because we have these overshoots here, where we overshoot our equilibrium population density for the infected individuals. We get to this point up here at the top, we get a peak in our epidemic. At that point, actually, our DI/dt is less than 0. So this starts coming down again. These recovery things here, these increases in S are due to our waning immunity. So as immunity starts being lost in the population, you get a buildup of susceptible individuals and you cross a critical threshold, at which point another epidemic can occur. And then it depletes those susceptible individuals again, immunity wanes, and then we start over again. Each time it's less and less big. Okay, there is another problem on this, which I will go through on Wednesday rather than wrapping it now. Okay, Friday even. What day is it? I don't even know.